So as a corollary, let n be a positive integer, and let n equals p sub 1 to the power of a sub 1 times p sub 2 to the power of a sub 2, and so on through p sub r to the power of a sub r be the factorization of n into powers of distinct primes then the integers modulo n is isomorphic to the direct product of the integers modulo the powers of those primes. So proof. Clearly, the powers of distinct primes are pairwise relatively prime. And so by the previous theorem, the direct product of the integers modulo the powers of those primes is cyclic, and therefore isomorphic to the integers modulo the product of those factors, which is the integer n. So let's look at an example. The prime factorization of 60 is 2 squared times 3 times 5. And so the integers modulo 60 is isomorphic to the product of the integers modulo 3 times the integers modulo 4 times the integers modulo 5, which in turn is isomorphic to the integers modulo 5 times the integers modulo 12, since 3 and 4 are relatively prime, and it is also isomorphic to the integers modulo 4 times the integers modulo 15, since 3 and 5 are relatively prime, and is also isomorphic to the integers modulo 3 times the integers modulo 20, since 4 and 5 are relatively prime. However, the integers modulo 60 is not isomorphic to the direct product of the integers modulo 2 with the integers modulo 2, the integers modulo 3 with the integers modulo 5, since the greatest common divisor of 2 and 2 is 2, which is not 1, so they are not relatively prime. So new theorem. Let the ordered n-tuple a1 through an be an element in the direct product of the groups G sub I if for every index I we have that a sub I has finite order R sub I in the group G sub I, then the order of the n-tuple the direct product is the least common multiple of the orders of each of the elements. So proof, let each element a sub I have finite order R sub I in the group G sub I. Then the n-tuple a sub 1 through a sub n to the power of m, which is the n-tuple that has as elements a sub 1 to the power of m and so on through a sub n to the power of m, is equal to the identity in the finite product if and only if the integer m is a multiple of each R sub I, which is the finite order of each of the elements in the n-tuple. Now, since the least common multiple of each of those orders is the smallest positive integer, that is a multiple of each of the orders R sub I, the order of the n-tuple in the direct product of the groups G sub I is the least common multiple of the orders of each element in its respective group. So now we have a new definition. For every integer r, such that r is greater than or equal to 0, that is, for every non-negative integer r, let z superscript r be the direct product of r copies of the group of integers where z superscript 0 is the trivial group, the group z superscript r is called the free abelian group of rank R. So notice that the free abelian group of rank R is generated by the set containing the elements e sub 1 through e sub r, where e sub I is the R tuple with 1 in the ith position and zeros elsewhere, that is, the jth component or jth coordinate of the R tuple E sub I is identical to the Kronecker delta. And hence the free abelian group of rank R is a finitely generated abelian group. Now also notice that for every group G, we have that G is isomorphic to the direct product of the trivial subgroup of the integers with the group G itself. Okay, so now we're ready to state the fundamental theorem of finitely generated abelian groups, and we will have to postpone the proof until later. And the theorem states, let G be a finitely generated abelian group then G is isomorphic to the direct product of a free abelian group of rank R times the integers modulo m sub 1 and so on times the integers modulo m sub n for some integers R m sub 1 through m sub n such that the integer R is greater than or equal to 0, and the integers m sub I are greater than or equal to 2 for every index I, and the integer m sub I plus 1 divides the integer m sub I for I greater than or equal to 1 and less than or equal to n minus 1. Further, the direct product is unique. Now, the direct product z superscript r times the integers modulo m sub 1 and so on times the integers modulo m sub n, satisfying conditions 1 and 2 in the fundamental theorem of finitely generated abelian groups is called the invariant factor decomposition of the group G the integer R, that is the rank of the free abelian group of rank R, is called the Betty number of the group, and the integers m1 through m sub n are called the invariant factors of the group. So notice that an abelian group is finite if and only if its Betty number is 0, that is, the group G is isomorphic to the integers superscript 0 times the integers modulo m sub 1 and so on, times the integers modulo m sub n, which in turn is isomorphic to the integers modulo m sub 1 through the integers modulo m sub n. In other words, every finite abelian group is isomorphic to the direct product of cyclic groups, where the order of a given cyclic group divides the order of the previous cyclic group in the invariant factor decomposition. Now, a group G is decomposable if and only if it is isomorphic to the direct product of two proper non-trivial subgroups. Otherwise, the group is indecomposable So let's look at an example. Let G be the integers modulo 6. Notice that the subgroup generated by the element 2 is the group containing the elements 0, 2, and 4, which is isomorphic to the integers modulo 3. And the subgroup generated by the element 3 is the group containing the elements 0 and 3, which is isomorphic to the integers modulo 2. So since the group G is isomorphic to the direct product of the integers modulo 3 with the integers modulo 2, which is isomorphic to the subgroup 2 times the subgroup 3, the group G is decomposable. Also notice that the only invariant factor decomposition possible for an abelian group of order 6 is the integers modulo 6. So by the fundamental theorem of finitely generated abelian groups, every abelian group of order 6 is isomorphic to the integers modulo 6. So as an exercise, let G be the direct product of the integers modulo 4 times the integers modulo 12 times the integers modulo 15. Determine the order of the ordered triple 3, 10, 9 in the group G. Determine what is the maximum order of any element in the group G. Determine, is the group G isomorphic to the direct product of the integers modulo 20 times the integers modulo 36? Determine the invariant factor decomposition of the group G. And finally, determine, is the group G decomposable? Okay, so we'll end here for today. Next time we will exploit the fundamental theorem of finitely generated abelian groups. So I hope you have enjoyed the 20th lecture. Thanks for watching.